Hello again, intermediate algebra students. Today we spend our second day on section 7.4, where we will continue to learn about the greatest common factor. Yesterday you learned how to find the greatest common factor. Today we are going to learn how to factor out the greatest common factor. I want to start though by looking at a quick little warm-up. So as always, go ahead and pause the video and find the greatest common factor of the polynomial written. Hopefully what you found is that the first term had 3 x's, the second one just had 1 times 5 and 2 x's, the third one had a negative 1 times 22, a 2 times 11, and 1x. So the only thing that all 3 pieces have in common is an x. So the GCF of this problem is just x. So that's what we did yesterday. Now we need to take that idea but go one step further and actually factor out the greatest common factor. You can see here that when you are asked to factor out the greatest common factor, you need to write the greatest common factor times what is left after you factor it out. So your final answers when we ask you to factor out the greatest common factor are going to be the GCF, parentheses, and then inside the parentheses you're going to write what's left of the original polynomial after you take that greatest common factor out. Now, one thing to keep in mind, the number of terms that your original polynomial has should be the same number of terms that is left inside the parentheses. Okay? All right, so we are actually looking at that exact same warm-up that we just did, except now the key word that's different. Instead of find the greatest common factor, it says factor out the greatest common factor. I'm going to rewrite what I had on the last one. And, oops, okay, so we had already circled that GCF was x. So if I was going to factor out the greatest common factor, I put that first. Remember, that's the GCF. But now I need to multiply it times what's left. And again, what we mean is what is left from each term. So since my original polynomial had 3 terms, I need 3 things inside this parentheses. So I start by looking at the first term. I had an x cubed, I used an x, but I have an x times x left. So I have an x squared left. In my next one, I have a 1, 5, and x left. So 1 times 5 times x is a positive 5x. That goes in the middle. And then I take my third thing. I had a negative 1 times 2 times 11, which gives me a negative 22. So if I ask you to factor out the greatest common factor, this is actually my final answer. X times x squared plus 5x minus 22. This is always going to be your first step of factoring. And when we get into the rest of chapter 7, we're going to learn that there's a whole nother layer. So today we are just focusing on the very first step of factoring, which is factoring out the greatest common factor. Okay, let's look at another example. So if I was given this problem and I was asked to factor out the greatest common factor, again, my first step is what we did yesterday, find the greatest common factor. Now, maybe you recognize, if you want to be more efficient, I recognize that 9, 45, and 36 are all multiples of 9. Okay, so I know right away that if I write this as 1 times 9, 5 times 9, 4 times 9, I know they have a 9 in common. So yesterday we talked about how there's efficiencies that you can do to help yourself save yourself some time. Having said that, if you didn't recognize that, you would have just ultimately broken all of these into 3 times 3. And then this would have gone into 2 times 2. So you can make that prime factor list, but again, then you would say there's a 3 and a 3. Now, there's 4 r's in the first term, 2 in the second, 1 in, oops, that's an r, 1 in the third. So they also have an r in common. So when I go to write my GCF, again, the difference is now that's just out front. I have a 9r. Okay, so they each have a 9 and an r in common. But again, we need to times it by what's left. So I go back to my first list. Okay, I already used the 3's. I have a 1 and 3 r's. 1 times r times r times r gives me 1r cubed. So just r cubed. I go to my second thing. And in that one, I have a 5 left up here and an r down here. So I have a positive 5r left. And last but not least, in this last list, I had a 2 times a 2. There's no r's left, so it's just plus 4. This is what it looks like when I factor out the greatest common factor. So that's the general idea. Now, once you get the hang of the general idea, the problem is there's one twist that will throw at you that you have to be a little bit careful of, and it adds a weird twist. If you have negatives inside the polynomial, you do what we talked about on the last one. Okay, so when we were on this one, when I had a minus 22, I just did a negative 1 times 22. And that's what made me realize I needed a minus here. There's one exception to that that makes it more complicated. Anytime the leading term is negative, Pearson, in particular, wants you to factor out that negative. Okay, and it's actually going to be important as we move into the next layer of factoring that once you have the what's left, you want the first term positive. So we're going to also practice the idea of always factoring out a negative if the leading term is negative. What I mean by that is when I go to break apart a negative 12, I start with negative 1 times 12. 12 is 4 times 3, 2 times 2. This one also has 3 x's. Now, I'm going to skip to the last term real quick because this one makes sense as well. It's already a negative. So I would do negative 1 times 27, 3 times 9, 3 times 3, and that one just has an x. The problem is the middle one has a plus. So if I just do it normal, I would do like 3 times 6 first. Having said that, as soon as the leading term is negative, we are always going to factor out negative 1. And so because of that, I am actually going to do something that seems a little weird. I know I need these 3 lists to have a negative 1 in common, so I'm going to make this have a negative 1. And I know that negative 1 times negative 18 is positive 18. And then a negative 18 is a negative 1 times 18. 6 times 3, 3 times 2. So it seems like an added step, and it actually is. Again, this part right here, when I did a negative times a negative, and then I had to break it apart again as a negative times a positive, seems a little interesting, and it is, I don't disagree. But again, it's only when this leading term is negative that we want to do that. Okay, so now again, our goal was to make sure we factored out a negative 1. They all have a negative 1. I look at all 3 lists, I see they also all have a 3 at the bottom of a branch. I think that's everything. Okay, now I also look at my variables and I see they have an x. About that phone call. So anyways, so we saw that they each have a negative 1. Oops. So if I was just writing the GCF, I would put a negative 1. We found they all had a 3. And they all have an x, which means my GCF is negative 3x. Again, our goal was to factor out a negative as soon as that first term is negative. All right, so I have the negative 3x times, and remember this is the what's left from each term. Now, when I look at this first term, now we have to be a little careful. The bigger our little trees get, we're only looking at the things at the very bottom of the trees. So this 12 up here, I don't care about because it has branches below it. So we have 2 times 2 times x left in that first one. So that gives me a 4x squared. My second term, again, at the bottom of the branches. Oops. This is at the bottom of the branch. The 18 is not, the 6 is not, the 3 and the 2 are. So I have a negative 1 times 3 times 2 times x gives me a negative 6x. Now notice, it started as positive, but when I factored out a negative, it changed the sign to a negative. Okay, and that's really what happens when you factor out a negative. You're actually just changing the signs of everything. So for the last one, again, I see a 3 at the bottom of a branch and another 3 at the bottom of the branch. No x's, and so 3 times 3 is a positive 9. Again, it started as a negative, it flips to a positive. The first one started as a negative, it became positive. Now here's one other tip when you're doing greatest common factor. You can always quickly check it in your head. If I multiply what I got here out, I should get the original. Now remember, we talked about a monomial times a polynomial, we use distribution. So if I do negative 3x times 4x squared, I do get negative 12x cubed. If I do a negative 3 times a negative 6, I get positive 18, and x times x is x squared. And finally, a negative 3 times 9 is negative 27, and then the x. Okay, so it's never a bad idea to quickly multiply it out in your head just to make sure that you did it right. Okay, let's look at one more example of this together so that I make sure you're getting the idea. Again, the key here is the leading term is negative. That's worst case scenario for you. That is where you have to break it apart as a negative 1 times 16, 4 times 4, and I can break all of these apart as 2 times 2. Now, had I looked at it ahead of time, I could have maybe seen that 16, 28, and 20 are all divisible by 4, so I could have saved myself some steps, but I like to show it both ways so you understand that you can keep going on the prime factors. Now, because the first term is negative, that's where whenever I have a positive, I have to do that weird thing. I want to factor out a negative 1, so I need to get that on the 28s list. So I make it a negative times a negative, which is the same as positive 28. But now I have this negative 28, so I need to make it a negative 1 times a positive 28. That gives me a negative 28. And now I can break it down as 2 times 14, 2 times 7. I'll go back and do my y's in a second. The negative 20 is a negative 1 times 20. Again, as soon as it's a minus, it makes it a little bit easier. 4 times 5, 2 times 2. All right, the first term had 6 x's, or 6 y's, I should say. 6. The second one had 4, and the third one had 3. You might be getting better at not having to write out all those y's. We know that the smallest exponent is going to be what it is, but it might help you now that we have to figure out what's left. So I'm going to factor out a y cubed, but now I have to find what's the same on each list. I have a negative 1 on each list because I made them have a negative 1. I have a 2 on each list, and I have another 2 on each list. And I think that's everything. So I have a negative 1 times 2 times 2 is negative 4 y cubed. Now, today's addition is we are multiplying it by what's left. So we go term by term. The first term, again, we're only looking at the bottom of the bottom trees. Okay, so I have a 2 times 2, which is 4. Y times y times y is y cubed. Now again, I can even check as I go. That first term, this GCF times the purple, should be negative 16y to the 6. Negative 4 times 4 is negative 16. Y cubed times y cubed is y to the 6. So that one's good. The second one, I see a negative 1 times a 7. So I get minus 7, and there's only one y. So minus 7y. Again, a quick check. Negative 4 times negative 7 is 28. Y cubed times y is y to the 4th. Check. Last but not least, I go to my last list. This is all covered. The only thing I see left is a positive 5 on the end. A negative 4 times a positive 5 is negative 20. Y cubed. We are good to go there as well. So this is my factored out polynomial. Okay, now that we've tried a bunch of different scenarios, I want you to pause the video and go through and do your best to solve these. When you have an answer, unpause to see how you did. I'm going to go the shortcut, and I recognize that all of these are divisible by 5. So I have 5 times 9, 5 times 7, and 5 times 6. Now, there are negatives in here, but not on the leading term. The leading term is positive, so I don't have to do that weird stuff. I guess what I should have done based on what we've been doing is a negative 1 times 35 and a negative 1 times 30 here. Sorry, forgot about that. 5 times 7, 5 times 6. This one had 5 b's, 2, and 1. So again, when I went to find my GCF, 1 b and a 5 on each one. Okay, so 5b times what's left, you should have had 9b to the 4th. minus 7b, because a negative 1 times 7 is minus 7b. And then finally, a negative 1 times 6 is minus 6. So hopefully you got 5b times 9b to the fourth minus 7b minus 6. And hopefully you kind of did the distribution in your head to check it. All right, number 2 was the one where we have that weird case where the leading term is negative. So I'm going to make that a negative 1 times 10, 2 times 5, 6x's. The second one, though, because it's a positive, that's when you have to do that really weird thing. A negative 1 times negative 8, because I need to put a negative 1 in there to factor out. And then negative 8 is negative 1 times positive 8, 4 times 4, not 4 times 4, 4 times 2, 2 times 2. This one's already negative, so I just have to do the one step. Okay, so you should have seen, because we made it, my GCF is going to be a negative 1, and then they all have a 2 in common. So my GCF is negative 2x times, the first list has a 5 and then 5x's, so 5x to the fifth. The second list has a negative 1 times 2 times 2, which is negative 4 with 1x. And the last list just has 2 2's, so that's plus 4. So we should add negative 2x times 5x to the fifth minus 4x plus 4. All right, so that's the skill word for today. Just a quick look at how we could see this in some pictures. Don't write this down, but Elenia is in charge of marketing for a travel company. She's designing a brochure that will have 6 photos. The photos can be arranged on the page in a number of ways. There are 2 main square photos, each of which have a length x times x on each side. So again, they're saying this is side length x and this is side length x. Okay, this one is x and this one is x. There are 4 narrow photos that are 1 by x. So this is 1, this is x. This is 1, this is x. So it wants to know the total area of the photos. Well, if this photo is x by x, that means this photo is x squared. This is 1x, 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 and x squared. So if I was just adding up like terms here, the area is 2x squared, and then there's plus 4x's. Okay, so that's a visual just to get us understanding what we're talking about, but we're going to use that to look at this next thing. So part B here says, find a rectangular arrangement for the photos. What factored expression represents the area of the arrangement? Okay, so first they started by placing all the photos in one row. But they want me to write the factored arrangement. So they're saying this is length x, and then this one, remember, is an x plus 1 plus 1 plus 1 plus 1. So this side is 2x plus 4. So if I wrote the area of this in factored form, I have length with it, which is x, times width, which is 2x plus 4. Okay, so this is a factored form of the area. Last but not least, if we rearranged it in as close to a square as we can, like they have on the right-hand side here, okay, so this is an x and an x, okay, so this is 2x, okay, because x plus x is 2x, and then this one is, this one is an x plus 1 plus 1, so it's x plus 2. So in this case, I would write factored form as 2x times x plus 2. Now, it says, which of these arrangements is more practical use of space? Well, this one's going to be because it's more compact. And here's the thing, you guys. These two things that we got, they are equivalent, meaning they get you to the same thing if we multiply them out. They get us to what we said the area of the whole is when we added them up. They both get us to 2x squared plus 4x if we multiply. Having said that, when you have the more efficient use of space, we took out the greatest common factor. The greatest common factor of it was 2x. X is a factor, but not the greatest common factor. Okay, last but not least, here's an example of how we can use what we just talked about to try to look at boxes and use factoring to find the side lengths. So we're kind of going backwards, right? We've used the box model where we put things on the outside and we multiply to get the middles. Now they're going to give you the middles, and they want to know, what is this length? What is this length? And what is this length? Well, in order to do that, you actually want to find the greatest common factor. So if I'm finding this side length, I'm finding the greatest common factor of 4x y squared and 6x squared y to the fourth. Well, if I use my strategy, this is 2 times x times y times y. This is 3 times 2 times x times 4 y's. Well, they have a 2 in common, they have an x in common, and they have 2 y's in common. So this side length would have to be 2xy squared. It's the greatest common factor of those. Well, since we know that length times width has to equal a box, 2xy squared times what is 4xy squared? Well, it's whatever's left, okay? So that 2 is left, that goes here. 2xy squared times what gives me the 6x squared y to the fourth? What's left? The 3 times x times y squared. So this is just a strategy to look at boxes in the box model to be able to find greatest common factors as well. All right, to summarize, just make sure you are now able to factor out the greatest common factor, because that is going to be the first step of factoring that's going to get much more complicated over the next few days. Here's a copy of the note sheet that I made as I was doing this, so if you didn't get anything on it, make sure you get that down, and don't forget to complete and submit your 7-4B Pearson practice. Thank you.